Okay, this is FS.C20, and basically it was asking us to continue some analysis on example FSAG. And what that one was about was analyzing basically the four different representations. This section is four subsets. So it was looking at the four subsets of this vector G. And it's actually part of two archetypical systems. The vector G is appended to this solution set and this solution set. So it actually makes archetypes G and H. G is consistent and H is not. And they asked us to perform some analysis using these vectors. And the first one we want to look at is we want to look at whether or not the solution set for G, basically, not the solution set, but the solution vector. We know this system is consistent, so we want to look at whether or not G can span it. And so we want to look at the column space of G and compare that with this solution. So I've done that in two different ways. First, by brute force, the column set of G can just be provided by the vectors for G themselves. In addition, we can use the BNS theorem in order to produce a simpler looking set of columns, which nonetheless spans the same set. So the question is, let's prove that these both span the set in such a way that they can produce this solution, because we know that the system with G appended is consistent. So let's take a look at it. We'll do this one first because it's a little bit easier. The reason why is it's linearly independent. We know that because we've got 0, 1, and 1, 0 here and here. So we can tell just what these column vector solutions need to be. For this system to be consistent, the second variable, which I'll just call G2, has to be 6. And right down here, G1 needs to be 20. So 20 and 6 are then the solutions to the coefficients that make this true. Let's check it on the other ones. Negative 20 plus 6, yeah, that's negative 14. Negative 20 plus 18, that's negative 2. And 3 times 6 is 18. So this guy all checks out. When we use these solutions, then this vector set produces this as an answer with these coefficients, showing that this is part of the spanning set when we use BNS to analyze the column space of G. Well, let's check out G brute force. And you can see the disadvantage of the brute force. If I wanted to check on the spanning set, this is not trivial. Like, I don't have any line here that shows linear independence, so I can't tell what the variables are right off the bat. And I can't use the old ones. This 6 and 20 actually don't work. I mean, I can show you 20 times 2 is 40 plus 18 is 56. That's not equal to 6. So if this works, it works by a different system. Well, it's a system of two equations with two unknowns. I'll arbitrarily pick the first two. So 2x plus 3y is equal to 6, and negative x plus 4y is equal to negative 14. So all we have to do is solve this for x and y. That gives us the two column coefficients, and then I can check and see that it solves for the whole system. But so we'll double the second equation and add them. So this will be 0, this will be 3, plus 2 4s is 11y, and that'll equal 6 plus 2 negative 14s, that's negative 28, that's negative 22, and that makes y equal to negative 2. So if y is negative 2, and we plug that in right here, that's negative 8 added to negative 14. When I add the 8 over there, I'll get negative 6. So negative x is negative 6. That makes x equal to 6. So supposedly this system uses coefficients of 6 and negative 2, whereas the old one used 20 and 6. But let's check these coefficients and make sure they work. We know they work in the first two because that's what we used to solve it. So let's check this one. Is 3 times 6, that's 18, minus 20 is negative 2. Yep. 3 times 6 is 18, minus or plus 2 is 20. Yep. And 6 times 6 is 36, minus 18 is 18. So far, it checks out. You'll notice something really interesting, and that is both of these coefficients used in the spanning set actually came from the solution set. And the same thing happened here. So I imagine if we were to develop alternate spanning sets that represented this column space, we would find that based on our selection of solutions that's what's unusual about this archetype. is that the solutions to the spanning set coefficients always turn out to be members of the solution matrix, which is kind of fascinating.